The electrical disturbances. Now we will see one electrical disturbance in this class or in this video. Electrical disturbances. Out of the different electrical disturbances, I am considering first one. First one is removal of one of the line in a double circuit. Removal of one of the lines in a double circuit by using this is the removal of the line forcefully, means we are intentionally removing one of the lines in a double circuit by using fast acting circuit breakers. First we will see what is the reason. If you understand the reason, then we can go for the actual discussion. Okay, so reason behind removing the line. First, if you understand this, you can understand why we are removing the line. Then we will see what happens when we remove the line, right? The reason behind removing the line is when, okay, let me write here, when the load on the synchronous generator increases. So there will be a difference. There will be a difference between generation and demand. Is it right or not? When the load on the system increases, there will be some difference between generation and demand. Now what happens, as the demand is greater when compared to generation, the demand is greater, it makes the speed of the rotor of synchronous generator reduces. Means when the load on the synchronous generator or the system increases, automatically the speed of the synchronous generator reduces, because there is a difference between the generation and demand happened. When the speed reduces, automatically frequency reduces. This is the thing which happens actually. Now when the load increases beyond, means when the load increases in a huge manner, suddenly increases in a huge manner, so there will be larger difference between PG and PD. PG minus PD will be larger. Whether it is positive or negative, it is negative, because demand is increasing, generation left at the same place. So as the demand is increasing further, as the load demand is increasing further, PG minus PD will be larger negative. So the speed will be much more reduced than the previous case. What happens? Frequency will be reduced much more. So there is a limit for frequency actually, which is a lower limit for frequency is 47.5 Hz. Okay, what is this? This is a lower limit of frequency. The lower limit of frequency is 47.5 Hz. When the load increases in a larger manner, it makes the synchronous it makes the speed of synchronous generator reducing in a larger manner. When it reduces larger, the frequency reduces, means it goes beyond 47.5 Hz. So you will have the system will lose the stability. Frequency collapse will happen. When the frequency is reduced below 47.5 Hz, there will be frequency collapse will happen. That is the reason why what we need to do is we need to, in those situations, we need to reduce the load. In order to reduce the load, we will remove one of the line. When we remove one of the line, the loads that are connected to this particular line gets reduced. means gets disconnected. In that way we can reduce the load. This is the situation where we want to remove one of the line forcefully in a double circuit. When the load is indefinitely increased, suddenly increased, which is beyond our control, what we will do is we will disconnect one of the line in a double circuit configuration forcefully by using fast acting circuit breakers to make the system, means to avoid the frequency collapse, basically frequency collapse. Okay, now we will see what happens when I remove one line. Let me draw the typical configuration of a radial network. See, we have let me take the help of a diagram. So this is the diagram. So this is the thing which you need to understand here. So this is the mechanical input, this is the synchronous generator, and this is the transformer, and this is a double circuit configuration, right? And this is a infinite bus. This is a synchronous generator. Now if you observe, how can you know, or how can you write the power transfer equation when you have both the lines? See, power transfer, I am assuming Pmax1 as, what is Pmax1? I am assuming the Pmax1 as maximum power transfer before removing the line, means before removing one line from the double circuit configuration, the maximum power transfer is Pmax1. Similarly, I am assuming Pmax2 as maximum power transfer after removing the line, right? Now observe the reactances. X1 equivalent now is nothing but equivalent reactance before removal. Before removing one line, X1 equivalent is the equivalent reactance. X2 equivalent is nothing but the equivalent reactance after removal. X2 equivalent. Now tell me, what is X1 equivalent? X1 equivalent is the summation of generator reactance plus transformer reactance plus transmission line reactance. Both the reactances are same, let us assume like that. So this reactance of the transmission line, equivalent reactance as XTL by 2. Now what is X2 equivalent? Again X2 equivalent is Xg1 plus X transformer 1 plus, as you removed one line you have only XTL. Now tell me what is the relation between X2 equivalent and X1 equivalent? X2 equivalent now can be treated as greater than X1 equivalent from these two equations. From the equation A and from the equation B, we can say that the equivalent reactance between the synchronous generator, this is the synchronous generator and this is the infinite bus, the equivalent reactance between the synchronous generator and the infinite bus is greater when we remove the line. Before removing the line it is lesser. When the equivalent reactance, means when X2 equivalent is greater than X1 equivalent, what about Pmax1 and Pmax2? Pmax1 Pmax1 is greater than Pmax2. just reverse, or you can write P max 2. Okay, let me keep it in simple. As x2 equivalent is greater than x1 equivalent, P max 2 is less than P max 1. P max 2 is less than P max 1. Since why this is happening? E and V are assumed as constants. As E and V are assumed as constants, and we know that P max 1 is given by EV by x1 equivalent, and P max 2 is given by EV by x2 equivalent, right? And from this we can say that P max is inversely proportional to x, is inversely proportional to x. So as x2 equivalent is greater than x1 equivalent, P max 2 is less than P max 1. That is the reason why, because of this reason, we have two power angle curves. We can analyze the equilaria criteria by using two power angle curves. Why we are getting two power angle curves? Because we have two different maximum power transfers. As we have two different, before the removal and after the removal, we have two different power angle curves, right? Now let me understand that before the removal, what is the relation between the shaft power and electric power? PS is equal to PE1 before the removal. So what is PE1 for a synchronous generator? EV by X into sine delta 0, right? And this is PS. EV by X can be EV by X1 equivalent, can be taken as P max 1 sine delta 0, and it is PS. From this we can find delta 0. From this we can find delta 0 as sine inverse of PS by P max 1. We can find delta 0 as sine inverse of PS by P max 1. Is it right? Before the removal of line from a double circuit configuration, the shaft power is equal to electric power. Hence the PS is equal to EV by X1 equivalent into sine delta 0. From this delta 0 can be found like this. Now after the removal, right? Now you have shaft power same, PS is same. Why PS is same? Because there is no mechanical disturbance. This is electrical disturbance. So PS remains the same. Whereas PE, what about PE? Now the PE is EV by X2 equivalent, right? X2 equivalent into sine delta 0 at the same angle. Now what happens? X1 equivalent is less than X2 equivalent, means X2 equivalent is greater. As this rises, PE reduced. As PE reduced, you have PS minus PE positive. PS minus PE positive is nothing but PA is positive. As PA is positive, we can call this as acceleration region, right? So that can be understood from the following figure. Okay, let me take the help of the figure. So this is the figure from which we can understand. Observe here. Okay, observe here. Previously we have this as the curve. So okay, PE1 is the power angle curve before line removal. Now what is PE2? PE2 is the power angle curve after line removal. After line removal as P max 2, and before line removal as P max 1. As P max 2 is less than P max 1, the height of the second power angle curve is less than the height of first power angle curve. Now point A is the stable point, means at this point the shaft power and the electric power both are same. So the synchronous generator is rotating in synchronous speed and delta is equal to delta 0. So we can call this as a stable point. What is this? This is a stable point. Now what happens is, suddenly the operating point moves from A to B. Why it moves from A to B? Because of the electrical disturbance, because of the line removal, the operating point moves from A to B. Now at point B, or from B to C, if you observe from B to C, if you are moving, the shaft power is this. The shaft power is shown by this line. This is the shaft power. Now what is the electric power? Electric power is below the shaft power. Is it right? As the electric power is less than PS, PS minus PE is positive. So PA is positive. Then it is called as acceleration. Because of the acceleration, omega increases, means speed increases. As the speed increases, delta increases. But speed increases beyond, means speed goes beyond the synchronous speed. Exactly at this point or at this point, the speed is synchronous speed. Now from B to C, the speed is increasing from omega s to omega max. Now at C, actually at C, what happens? At C, you know that already from the previous case studies, we can understand at C, though accelerated power is 0, omega is equal to omega max. Then we can call this point C as oscillating point. As the C is oscillating point, due to moment of inertia, it reaches up to D. Right? Now again from D to C, it is the swinging back. So this area is called as decelerating area. Why it is called as decelerating area? This is the shaft power and this is the electric power. Electric power is greater than the shaft power. So PE minus PS, PS minus PE, not PE minus PS. PS minus PE is positive, as the electric power is not positive, very sorry, it is not positive, it is negative. As PS is lesser, PE is greater, so PS minus PE is negative, which indicates PA negative. As PA is negative, this region is called as decelerating region. So this area is called decelerating area and this area is accelerating area. First the operating point move from A to B suddenly because of the electrical disturbance. Now it moves from B to C. As the C is not a stable point or it is a oscillating point, the swinging continues up to D. So again the swinging means there will be a swinging back from D to a point which is greater than B. Then again it swings like this, then again it swings like this, then again like this, then again like this and like this. Finally it reaches a final delta. So that delta value is delta 1. Okay, delta 0 is previous load angle before the line removal. Now what is the load angle after the line removal? So new load angle or new stability angle, right? So finally the delta value as shown previous, like this. Here it starts at A. Now this point is C. And this point we considered as D. So it oscillates between A and D like this, and finally settles at C. This is the difference. Okay, so this is about the application of equal area criteria for electrical disturbance. Means sudden removal of what is the electrical disturbance? First electrical disturbance, sudden removal of one of the lines forcefully in a double circuit by using fast acting circuit breakers. Okay, so related to this electrical disturbance, we will solve a problem, and this is the last one for today video. This is the numerical problem which we will solve in this video. This is a very important and a very simple problem, and this problem asked many times in the examinations. Right, now see the question. Please go through the question along with me. So a 100 MVA 11 kilovolt. Okay, this problem is basically related to the removal of line, sudden removal of line from double circuit configuration, as we have studied the electrical disturbance in the previous video, right? Not in the previous video, in this video. So the question is a 100 MVA 11 kilovolt 50 hertz 4 pole synchronous generator is connected to an infinite bus by a lossless double circuit line. This is mainly based upon means it looks like this. You have a synchronous generator which is connected to a transformer, and it is connected to a double circuit line, and this double circuit line is ended with infinite bus. This is the circuit configuration actually given in the problem. Now the inertia constant of the machine is 6 megajoules per MVA, which is H value. The electrical output delivered by the generator to the infinite bus is 30 megawatts. The maximum power of each line in a double circuit line is 40 megawatts, and here one of the line in the double circuit configuration or a double circuit line is removed forcefully. The synchronous machine is having acceleration. The acceleration is maintained for 10 cycles. Next, we need to find the position of the rotor in electrical degree with respect to reference axis at the end of acceleration period. We need to find this for the given problem, right? How can you solve this? See, first in order to find the position of rotor at the end of this acceleration period, we need to know the change in delta value. So the final value of delta is given by delta naught plus delta delta, where delta naught is the load angle before the disturbance. Here the disturbance is nothing but the sudden removal of line. So before removing the line, the load angle is delta naught, and delta delta is nothing but the change in load angle, during the acceleration period, right? So delta delta now is nothing but change in load angle during the acceleration period. The acceleration period is basically maintained for 10 cycles. We should know what is the time required for 10 cycles if the frequency of the signal is 50 hertz, right? So we need to find this change in load angle and delta 0 to find delta. In order to find delta, we need to know delta naught and delta delta. Now how can I find delta naught? It is obtained from the basic condition before the disturbance, where the electrical power is equal to shaft power. The electric power is equal to shaft power, and the electric power output delivered is given, which is equal to 30 megawatts. 30 megawatts, is it right? Now what is the shaft power? Shaft power is also equal to 30 megawatts. Now 30 is nothing but P max into sine delta 0. So this 30 megawatts must be equal to P max into sine delta 0. Now let me write it here. So shaft power is same as electric power. As the electric power is 30 megawatts, shaft power is also equal to 30 megawatts before the disturbance. So it is 30 is equal to P max. What is the P max supplied before the disturbance? Here if you observe in the question, the maximum power of each line in a double circuit line is 40 megawatts. Now for the two lines, it is 40 plus 40, because if each line is supplying 40 megawatts, both the lines combinedly supply 80 megawatts, 40 plus 40. Hence the Pmax value before the disturbance. In order to find delta 0, we need to take the Pmax value before the disturbance. So it is equal to 80 into sine delta 0. So from this equation, okay, 30 is nothing but the shaft power, and 80 is nothing but the maximum power transferred before the disturbance. So this equation is very important in order to find the initial load angle. So let me take in a separate page. So 30 is equal to 80 into sine delta 0, where delta 0 can be given by sine inverse of 30 by 80. Sine inverse of 30 by 80. So now delta 0 comes out to be, if you calculate, please calculate along with me. So delta 0 or delta naught is given by 22 degrees. This is the initial load angle, means before the line removal. Now delta is nothing but the change in load angle. What is delta? Change in load angle during the acceleration period. In order to know the formula for this, I request all of you to go through the previous videos or previous classes of me. That's why I am repeating again and again. Please go through the videos in order. Now from the previous video we can understand that delta is given by alpha into delta t whole square by 2, where alpha is nothing but the angular acceleration. So what is angular acceleration? It is d square delta by dt square. Now from the swing equation we know that m d square delta by dt square is equal to pa accelerated power. This is from the swing equation, we know this relation. Now from this, how can I find alpha, which is d square delta by dt square? It is equal to pa by m. Is it right? Now first we need to know accelerated power, then we need to know moment of inertia, which is m, then we can find pa. Now accelerated power is nothing but shaft power minus electric power. Shaft power minus electric power. Now it is the electric power during the disturbance, PE2. PE1 is nothing but the electric power before the disturbance. It is same as shaft power. Whereas during the disturbance, the electric power will change. So PS minus PE2 is equal to PS minus PE2 by SH by 180F, because m value is given by S into H by 180F. If I want to express alpha in electrical degree per second square, I will take 180. If I want to know alpha in electrical radian per second square, I can keep pi, right? So in order to know, you should know what is PS and what is PE2, what is S, what is H, what is F, all these we need to know. Okay. What is PS before the disturbance 30, and PE is 40, right? So let me take a fresh page so that we can do it in a neat manner. So in the fresh page I am starting. So alpha is equal to Pa by m. Alpha is equal to Pa by m, and it is equal to shaft power minus electric power. What is this electric power? Electric power during the acceleration period. So we can call this as electric power after removal of line, because after the removal of line only we will get the acceleration. So after the removal of line by sh by 180 times f. So this is electrical degree. So the unit of alpha is electrical degree per second square, angular acceleration, right? Now alpha is equal to ps is 30 before the disturbance minus before the disturbance electric power is same as shaft power, and electric power is 30, so shaft power is 30 minus it is PE2 because after removal what is PE2? It is P max 2, is it right? P max 2 sine delta 0. P max 2 now means when one line is removed you have only one line and that line is transferring 40, so 40 sine delta 0. Why I am taking delta 0 here even though I am finding alpha during acceleration? Because we should know the initial angle. From the initial angle only we will get what is the acceleration from that angle, right? So that is the reason why I have taken delta 0 as 22 degrees, which we have determined, right? And these are the things which are given: apparent power of machine S, and inertia constant of the machine as 6 megajoules per MVA. So 100 into 6 by 180 into 550, is it right? Now alpha is equal to, please calculate along with me, take your calculator and do this. So you will get 225.2 degree, sorry, it is not actually degrees, 225.2 electrical degree per second square, 225.2 electrical degree per second square. This is alpha value. Now when you know alpha value, you can find delta delta easily by using the formula alpha into delta t whole square by 2, right? Now what is alpha? It is 225.2 into delta delta, it is the change in time. So because here the acceleration period is maintained for 10 cycles, 10 cycles means 0.2 seconds, so you will get 0.2 whole square, right? So in order to find delta t, you need to take the concept of the frequency. Frequency f is equal to, f is nothing but number of cycles per second. If frequency is 50 hertz, it indicates that there are 50 cycles per second. For 1 second we have 50 cycles. If I want to know the time taken for one cycle, I can divide this with 50. So from this I can find the time taken for one cycle. Time taken for one cycle is given by 1 by 50 seconds. If I want to know the time taken for 10 cycles, it is 10 by 50. So 10 by 50 comes out to be 0.2 seconds. That's why it is 0.2 whole square by 2, right? Now this is change in delta in electrical degrees, as alpha is taken in electrical degrees only. So you will get delta 4.5 degrees. Now what is the final value of delta? Means the change in angle, because why the delta is changing? Because of the acceleration, the delta value increases from delta 0 to delta. The see here, delta is nothing but the position of rotor in electrical degrees with respect to reference axis. We have repeated this for many times, that load angle, torque angle, power angle, all are same, which is the angle between the rotor and synchronously rotating reference axis, right? This is delta value. Now delta final can be given by delta 0 plus delta delta. So delta 0, we know that it is given by, we got this as 22 degrees plus 4.5. So it comes out to be 26.5 electrical degrees basically. See, if in the examination or in the question, if it is asked to find delta specifically in mechanical degrees, as you have the relation between the electrical degrees and mechanical degrees as theta m is equal to 2 times theta e by p. You know that relation between the electrical and mechanical degrees. So you can use that relation to find mechanical degrees. So this is the question asked in previous year question papers. More times this question is asked. That's why I told you this is a very important and a simple question to answer. Though it looks lengthy, the logic is simple. If you have any valid doubts, please post them in the comment section. Thank you very much.